Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Okay, so quick re-record after some of you clever people realise I got the very first calculation wrong in the previous upload. So let's try this again. Right, here is the solution to exercise 3. Hopefully, okay? This follows the episode 6 video where we looked at the maximum demand of diversity, and we're just going to do this third scenario of a small catering shop. The scenario includes 2 light circuits, one with 24 times 58 watt fluorescent luminaires, one with 8 pendant sets, and 2 500 watt PIR floods. There are 4 cooking appliances. Remember, this is a catering shop, so we're not going to think of household type of use. We're going to think of, full demand use. So they'll be powered with separate circuits. There is a requirement for 3 power appliances, which are coffee machines, and at the time we'll look at the best way to wire them up, and 4 socket outlet circuits of radials. Now, remembering from the on-site guide, we're going to use the demand table, which is table A1, very first appendix in the on-site guide. This table is to assess the demand of a final circuit. Okay, so we apply it to lighting outlets in this case, so we'll be looking at the equivalent load for everything except for lamp holders, where it says 100 watt for every single lamp holder, because we still assume 100 watts at the moment, apparently. You'll also see under this table in the on-site guide, in the note, it does mention that when you have discharge lighting, to consider a 1.8 factor due to the harmonic content and harmonic effects of the control gear, unless you have manufacturer's information. So that's probably all we're going to use this for. I think other stationary equipment, British standard, so the 3 kilowatt power equipment, this isn't applicable, and the household cooking appliances are not for household purposes, so we're not going to use those for that. We'll use table A2 a lot. This is the column we're going to use, the small shops column. So we do this with the lighting, and then we'll do this with the power circuit, the cooking appliances, and then down here for the socket outlet arrangements. Okay, so let's go back to them. First one, light circuit, 24 times 58 watt fluorescent luminaires. So break that down, and here's some adjusted math, because apparently I got this wrong earlier. Right, 24 times 58 watts, and we're going to apply the power factor of 1.8 because the book says so. Now remember, the 2396, the marking criteria the assessors will use at a starting point is going to be the on-site guide, the electrician's design guide, the IT documentation, the information everyone has access to. If you choose to use a different factor in your designs, you're going to have to make sure you attach that data so that the assessors or whoever reviews your design can see that. It's kind of creating work for yourself, but it's probably more accurate to do it that way. Alright, so in this case, 2506 is the wattage over 240 volts. I've gone with 240 volts because why not? Let's assume they're old light fittings that are power rated at 240 volts. You'll probably go with 230 volts in your designs. That's what you probably should do. That gives us 10.44 amp. We'll throw that over here for now. Let's go to the next light circuit. 8 100 watt lamps. Again, 100 watt lamps we're not supposed to be able to buy anymore. They still exist in circulation here and there, but really, you probably could assume a lesser demand for that. That would be more than acceptable, I would have thought. But the book says 100 watt for a lamp holder, so it's 800 watt. And 2 500 watts, which is a kilowatt. 1800 watt total, over 240, 7.5 amp. And we'll throw that up there as well. So those are 2 circuits. Those are the 2 demands of those circuits. We haven't applied diversity yet. The cooking. Now, We're not going to apply the household idea because, again, this is a catering shop. The cooking equipment is most likely installed for purpose. However, we can diversify the circuits. We don't diversify the final circuit. If a piece of equipment says it needs this power, a circuit will be installed to supply that power. We don't assume they'll use a lesser amount of power. What we may do for the distribution to the board feeding those circuits is assume those circuits may not be used at the same time. And we'll see this with diversity a little bit later. But for now, we just need to work out the full power demand of each of these cooking appliances. So the largest one, 16 kilowatt, which is, at 240 volts, that's pretty stupid. That is 66.6 amps. Now, you're thinking, okay, well, not a 32 amp socket, it's not a 63 amp socket. Is it 125 amp socket? Is it fixed? No. What you'd probably have in the real world is a three-phase piece of equipment, and that would drop it down to 23.1 amp, because IB is the square root of is power over the square root of 3 times 400. So you can see just in this little example why sometimes when equipment requires a much larger amount of power, it's much better for demand. It's much better for for cable costs and everything, to put on three phases to lower the demand on the installation. That's a big drop, but we're staying on single phase, so we're going to put 66 over here. The other two appliances, 4000 at 230 volts, 17.39 over here, and 2 kilowatt at 240 volts, 8.3 over here. This is just simple P over V. The next circuit, power. Now this is the questionable area really. It's 3 times 3 kilowatt coffee machines. Now 3 kilowatts at 240 volts is 12.5 amps. So it's you could think of it as 3 fuse connection units, which you would probably be more than happy to put on a radial arrangement. The issue here is, if you remember this table before, this here, other stationary equipment, it just takes the normal current into account. We can't diversify a single item of electrical equipment here. We can't diversify the equipment for its final circuit. So we have to assume full demand. So in this case, that's 9 kilowatt. Now 9 kilowatt over 240 is 37.5 amps. So that's a lot of demand for a single circuit. So what we're going to do right now is assume it'd be better to apply diversity to the circuits if we had them as 3 separate circuits, and that might allow us to drop that current down. So what I'm going to say is it's 37.5 amp total demand, because we can't diversify the demand of the equipment, but if I split it between 3 circuits, I may then be able to diversify the circuits themselves. So I'm going to put that 37.5 as 3 separate 12.5 amp circuits. That's my suggestion. Socket outlet radials, no diversity to a final circuit arrangement. You just put 20 amp through. Okay, so those final circuits themselves aren't allowed for diversity. But what we can now do is allow for diversity on the whole installation. So for lighting, if we go back to this, now we're going to be looking at this table. For lighting, we can take 90% of the total current demand. So the 2 circuits of lighting equals 17.94 amp. 90% of that times 0.9 drops it down to 16 amp. So we saved just under 2 amp. Wow. Next, cooking appliances. If you go to that table, it tells you take 100% full load of the largest, 80% full load of the second largest, and then 60% full load of all of the remaining cooking appliances. So in this case, we're going to have to take 100% full load of that big 66.6 amp. That's still not ideal, but we've got to. We'll then take the second largest, which was the 17.39 amp, and we'll apply 80% to that. 17.39 times 80% brings that down to 13.9 amp. Slight shaving there. And then the remaining, well in this case there's only one left, 8.3 amps, we take 60% of. So 8.3 times 60% is 4.98, and we'll add all those together. And that'll bring us 85.48 amps, which we'll go over there for diversity. Next, the power circuits. Power circuits, which is right at the bottom of that table, you'll see it says you take 100% of the full load of the largest appliance, then 75% full load of all the remaining. Well, they are of the same demand, so you just take one of them, 12.5 appliances, and you put that aside, and then the remaining two, which is two of them is 25 amps, you apply 75% to. So 25 times 75% is 18.75. Add that 12.5 back, 31.25 amp. Throw that up there. So this is diversity for the lighting, the cooking, and the power. Next one, socket outlet circuits. Now this is where we're going to say, right, this is to the arrangement of Appendix H, which is fine. If you look at the actual table, which is on the next page of the on-site guide, it tells you for small shops and catering, small offices and things, we take 100% current demand of the largest circuit. Now again, this could be a 32 amp ring with a 20 amp radial next to it, so you take the 32 amp. Yeah, but in this case they're all 20, so we take 100% of the largest, a 20, and 50% of the remaining. So we have the 4 20 amp circuits. We take 1 20 amp out, leaving us with 3 20 amp circuits, which is 60 amp, and we do half of that, which is 30 amp, and we add that 30 amp back to the 20 amp, 50 amp. Okay, this is diversity with power circuits. Just actually going back to this one, remember earlier on we said it was 37.5 amp, wasn't it? If we did it all on one circuit. By applying diversity, we have managed to drop that a little bit. So going on a single circuit basis for each of those has worked out better. Okay, circuit demand, overall diversity, the total of that, there we go. So for this small catering shop, we're going to require a supply that can accommodate a maximum potential demand of 182 amp. This is purely down to their cooking demand, really, of, as you can see, of 85 amp. Now remember, if we bunk that down to 3-phase, we'd be taking 40 amp off of that. That's good, but it's still well over 100 amp. So if they had a 100 amp supply, then you could question it might not be large enough on a 3-phase. I mean, it would be fine on 3-phase because you'd take all the other loads off of the phases, so it'd probably be fine. But for single phase, 100 amp is no good. So if there is a single phase supply on this existing catering unit and it has 100 amp on it, it clearly probably wasn't a catering unit before and it's been changed of use or something, then they're going to have an upgrade to their supply. Most likely though, small catering shops, you'll see 100 amp supply, but it'll be 3-phase, and all this will be balanced on those phases. This just shows you the importance of having 3-phase systems on little shops, little catering units, etc. But here's our answer. Here's our result. Okay. Again, thanks to a couple of guys who mentioned, who literally took seconds to say, "Oh, that's not right. That's not right." It's good that you guys can see these and immediately crunch numbers and say that's wrong, because that's there's no point in you all just going, "Oh, this must be right because it's on YouTube." Well done with that, and I will probably. I mean, we've had like 7 2396 videos, I think, probably on the spin. So I'm probably going to take a break from the 2396 as I prepare outcome 4, because I want to do another video next on. I want to discuss grouping factors again, because I'm seeing some evidence of it not being considered a lot. And also do another video on the Wine Regulations 18th edition, because they've just announced what's coming out in the 18th edition just last week. So I just want to do a little video on that, and then we'll pick up 2396 again. But thank you guys, and I apologise for the delay in this and it being re-uploaded. But thanks a lot, and I'll see you soon.